All right, here we have the mother of all gas laws, the ideal gas law. And it really does combine all the variables that we've been looking at throughout the entire gas unit. And those variables have been described as Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law. But with all those little baby gas laws, you could only look at comparing two variables and then everything else had to be constant. But this ideal gas law lets you look at all variables in one beautifully packaged equation. Now, hiding in this equation are Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law. It's all in there. But you can compare all these variables at once with the ideal gas law. We always call it PV. PV equals nRT, where P obviously stands for pressure. We're going to use kilopascal. V is volume. Often it could be liters or milliliters, but we will use liters in this case. N stands for number of moles. So we kind of looked at moles with that Avogadro's law. The number of particles is related to the volume. R is a gas constant. What? That's maybe the only one that's kind of weird. The gas constant. 8.314 liter kilopascal per mole Kelvin. Now, sometimes you might see it looking kind of like this. 8.314 liter kilopascal per mole Kelvin. And it really is a constant. Now, there are different values of R, the gas constant. They'll change depending on the pressure unit that you're given. So most often we measure our pressure in some kind of a metric unit. So the value of R that we'll use is this 8.314 with kilopascal. And if for some reason we're doing a problem and maybe the pressure is in atmospheres or millimeters mercury, then there is a different value for R, and I would just give it to you. But the value of R is a constant. It's something you look up. I give it to you. I'm going to put it on the test. Nothing that needs to cause you any harm. But the other variables need to match the units of the gas constant R, which is why we're going to use liters for our volume, kilopascal for our pressure, N stands for moles, and T is temperature, and it does need to be in Kelvin. Any gas law has to have temperature measured in Kelvin. Okay, cool. So here we go. It's just a plug and chug kind of deal, right? Some cool things that come out of PV equals nRT. Number one, all the little baby gas laws are hiding in here. So before, when we were looking at, let's say, Boyle's law. Remember Boyle's law? Like P1V1 equals P2V2. And we said that you had to have a constant number of particles and a constant temperature. That's kind of reflected in this equation, that pressure times volume needs to equal a constant. Well, this is everything that would need to be constant. N is moles, R is like your gas constant, and then T is your temperature. That needs to be constant. So Boyle's law is kind of hiding in there. You could rearrange this equation, like do a little algebra. And say you were to solve, I move over temperature, hiding in this equation. Here would be Gay-Lussac's law, pressure over temperature. But then I would be moving my volume over to the side. That would be constant if I finished my algebra. So I'd have to have constant moles and constant volume. Or hiding in here, V1 over T1, volume over temperature, Charles' law. But then I'd have to move my pressure if I finished my algebra. And so I'd have pressure and number of moles on the constant side. You can plug this in and solve for that 22.4, that magic number of Avogadro's law. Avogadro's law said that 1 mole of any gas at standard temperature and pressure is 22.4 liters. You can prove it. pressure is about 101.3 kilopascal. V, volume, let's solve for it. N, 1 mole of any gas. R is the gas constant, 8.314. And T is temperature, but it has to be in Kelvin. So standard temperature is, I can squeeze it in here, 273 Kelvin. So all I did here is like plug into Pervner, the ideal gas law, the conditions at STP, standard temperature, standard pressure, and I'm solving for the volume of 1 mole. If you plug this in your calculator, just for kicks, I'm going to solve it. Okay, so 1 times 8.314 times the 273 divided by 101.3. Oh my gosh, that's like 22.4. And now that would come out in liters, because the other units have to match the units of my constant. So it's all of these bad boys. Liters, kilopascals, moles, and Kelvin. So this is the volume of 1 mole at STP. Standard temperature is, and standard pressure is 101.3 kilopascal. It's like all these little gas laws are hiding inside of this Pervner, this ideal gas law. It's fabulous. Now, for the most part, it's plug and chug. The times that I need Pervner are when I have lots of different variables. So I see liters and Kelvin and kilopascals and moles. Oh gosh. That's when I'm probably thinking Pervner. Okay, so average lung capacity in humans is about 4 liters. At 300 Kelvin, which really is about normal body temperature, and 110 kilopascal, how many moles of oxygen could your lungs hold? How many grams of oxygen can your lungs hold? And so again, when I see lots of data, lots of different variables, that's when my mind starts drifting towards Pervner, the ideal gas law. But it's just plug and chug. P is my pressure, 110 kilopascal. V is my volume, 4 liters. N is my moles, that's what I'm solving for. R is my gas constant, which I will give you, 8.314 liter kilopascal per mole Kelvin. I'm going to give you all of that to remind you that your volume needs to be liters, your pressure is kilopascal, N is your moles, and T, your temperature, must be in Kelvin, which it is. But now, I mean, this isn't bad, right? Now it's just algebra, plug and chug. Okay, so I want to solve for N. So I'm going to take my 110 times 4. And then to get N alone, I'm going to divide both sides by the 8.314 and divide by the 300. Boom, got it. Now for sig figs, again, I'm not super crazy. All of this data has 3 sig figs, so I'm cool with 3 in my moles. 0.176 moles. This is oxygen gas, which is diatomic. O2. Isn't that nice? So easy. I'm almost like kind of sad. The gas laws are about done. This is the last one. This is plenty of gas laws. Plug and chug. Okay, so if you can solve for moles, I know we can solve for grams. You're never going to escape moles and grams. How many grams of oxygen can your lungs hold? Not that you really care, but I mean, if you did, now that you have moles, you can just set up a little switch. Cancel moles of oxygen. We want it in grams. The periodic table tells me the mass of 1 mole, but again, because it's diatomic oxygen gas, my mass, my molar mass, does need to be diatomic. So instead of 16, 32. 0.00 times 32. Fabulous. 5.65 grams of oxygen. Yeah, there's like some interesting trivia for you, I guess. 4 liters, that's about average lung capacity. Nice. So now like a basic question might just end at, what's the value of N moles? How many moles? Then to get a little more proficient, maybe they'll ask you, now switch that to grams, where we're connecting the dots between gas laws and mole calculations. It's fabulous. They might ask me how many molecules of oxygen are in my lungs. I could multiply by Avogadro's number, 6.02 times 10 to the 23rd, if I had moles. So that might be like a proficient extension. Please, I know you could do that. Maybe something else that might be a little more along the proficient lines. Something like this second example. A 500-gram sample of dry ice, which is solid carbon dioxide, vaporizes to a gas at 25 degrees Celsius and 975 kilopascal. What volume will the gas occupy? 500 grams of dry ice, that's kind of a lot. Okay, so I see lots of data. I see masses and temperatures and pressures, and they're asking me for a volume. So again, I'm thinking perfect. I'm thinking my PV equals nRT. P is my pressure. We're using kilopascal, which I have. V is my volume, which is what I'm solving for. Okay, but now here's where maybe this one becomes a little more proficient. N stands for number of moles, and I don't have that. I have a 500-gram sample. So I'm going to need to do a little sidebar here and get that 500 with a decimal, 3 sig figs. 500 grams of carbon dioxide, dry ice. I need to get that out of grams and into moles. So this time I want moles, so moles goes on the top. And the mass comes off my periodic table. So I add carbon and 2 oxygen. A hair over 44. 500 divided by 44.01. And so the 500 with the decimal spot has 3 sig figs. So let's go 3 sig figs, 11.4 moles. Aha! Proficient! N is my moles, 11.4. R is my gas constant, 8.314. And again, I'll give you all these units. It's liter, kilopascal, per mole, Kelvin. Which kind of reminds me that my temperature needs to be in Kelvin. Aha! So again, why this one might be a little more proficient. I need to take this 25 degrees Celsius and add 273 to switch her to Kelvin. Okay, so 298 Kelvin. But now this is plug and chug, right? Now I can handle this. Okay, so let's combine my 11.4 times 8.314 times 298, and then we'll divide both sides by the 975. Got it. Oh, let's see here. Maybe like 3 sig figs. Most of my data has about 3. It's like 28.96. Let's go 29.0. 29.0. And the volume would be in liters, because liters was the unit used in the constant. Proficient. So basic, plug and chug. Basic might just end at, hey, solve for the moles. I didn't have to do anything else. All the other variables were in the right unit. Proficient, I might have to switch some units, switch some grams to moles, make sure my temperature's in the correct unit. And advanced. Something like this guy. An unknown diatomic gas has a density of 3.167 grams per liter at standard temperature and pressure. What is the identity of the gas? Heck if I know. I guess I could take an educated guess if it's an unknown diatomic gas. Okay, so this is going to come up every now and then. Identifying an element, and identifying a gas, could be anything. One of the best ways of identifying an unknown is by calculating its molar mass. Molar mass. Is grams per mole. So I look on the periodic table. The molar mass of helium is about 4 grams per mole. If I were to calculate a molar mass of 4 grams per mole and they told me that it was an unknown noble gas, I would just go to the periodic table and match it up. Oh, it's helium. So it's a great way of identifying an unknown element. Or it could be a compound too, for that matter. There's a couple of these in our near future as well, so we're going to practice these. Molar mass, grams per mole. Identify an unknown. Great. So how is this data supposed to give me the molar mass, right? Okay, so I'm given density. Density is 3.167 grams per liter. Well, that's kind of like saying that 3.167 grams is the mass of 1 liter. Grams per liter. Mass for 1 liter. Oh, grams. I could use that. And to do molar mass, I need grams. Here's the grams. 3.167 grams. But now I need moles. And for that, let's do pervert. PV equals nRT. Aha, okay, so here's the advance. There's a lot going on here. P is my pressure. They tell me that it's at standard temperature and pressure, and then they give me standard pressure, 101.3 kilopascal. Volume. Okay, here's usually where people get tripped up, because they never really come out and tell you a volume. But it's hiding. It's hiding in the density. That 3.167 grams is for 1 liter. 1 liter is my volume. Oh, 1 liter. And I get too picky on sig figs, so I don't know if you want to go 1.0 liters or just 1. In the end, we'll just leave something kind of reasonable here. PV. N is what I want to solve for. R is my constant. 8.314 liter kilopascal per mole Kelvin. T is my temperature, but it does need to be in Kelvin. So instead of 0 degrees Celsius, I need 273 Kelvin. Boom, moles. Solve this bad boy for moles. Now be careful with your algebra too. I mean, sometimes people have just goofy little algebraic errors, which is obviously why you show all your work. And so in a sense, I'm taking 101.3 times 1. And then I'm going to divide both sides by the 8.314. And I'm going to divide by the 273. All right. So I get a number. It's kind of small. It is 0.044, maybe 6 moles. When in doubt, I kind of like 3 sig figs, 4 sig figs would be fine. Okay, so there's my moles. I can do molar mass. Molar mass was grams per mole. I knew the mass because they gave me a density, which is a ratio of grams per volume. Then I used that volume in the pervert to solve for the corresponding moles. 0.0446 moles. Okay, so now we cross our fingers that this comes out to be a diatomic molar mass. 3.167 divided by 0.0446. Okay, it's like 71. 71.0. And that's grams per mole. Okay, so now we need to identify the gas. An unknown diatomic gas. Diatomic means that there's two atoms. Oh. So if I take this 71 and I divide it in half, do you see where this is going? I get about like 35.5. That would be like the mass of one atom of this element. If I look on the periodic table for the element whose molar mass is closest to 35.5, it's chlorine. Is chlorine diatomic? Game on it is. Yeah, this is chlorine. Cl2 would be the diatomic version of chlorine gas. And so, yeah, if I took the individual molar mass, it would be about half of that. 35.5 times 2, 71. Isn't that awesome? So now that's like an advanced example where there's a lot going on. Where if you had any little piece of the puzzle wrong, you'd be showing all your steps, and I can award you partial credit. There are some great examples of how you can apply this ideal gas law perv nerd. We're going to go in the lab with this guy too. We're going to do a couple labs where we can solve for different variables and use lab data to confirm that this perv nerd, this is the real deal.